So our error theorem tells us how far off we can be when we make a partial sum. Here they want us to find the 55th partial sum. So S55 is the sum as k goes from 1 to 55 of 5 over k to the 6th. All right, I like to list a few terms sometimes to kind of wrap my brain around it. So if k is 1, first term is 5, second term is going to be 5 over 2 to the 6th. Next term is going to be 5 over 3 to the 6th. And we're going to keep adding those up until we get to 5 over 55 to the 6th. So that's a partial sum. The actual sum S keeps going. So S, the real sum, starts the same way. Passes by this 55th term, calculate the 56th term, be a 6 there, and it just keeps going. These terms I didn't add up in the partial sum, the 56th term on, that's the remainder for the 55th term. So we call that R55. And that right there is our error. The integral theorem remainder part says that that error, that remainder, is going to be between two integrals related to the x version of this function here. And we're going to have an n on that side and n plus 1 on that side, and they go to infinity. So this would be 5 over x to the 6th dx, same thing here. Now, I didn't use the integral theorem up front to show that this converges, because it's a p-series and p is greater than 1. Right, so it is a convergent series because it's a p-series. So to figure out bounds on the remainder, and here they're really only asking for the upper bound right there. So the remainder for the 55th sum is going to be, let's see, what do we have for an antiderivative here? We would view that as 5x to the negative 6th. So then the antiderivative would be 5x to the negative 5th over negative 5. So we get some nice cancellation there. And we need to evaluate that. Our n here is 55. And for the infinity part, we're going to have a limit. So then we're going to get the limit as x goes to infinity. This is going to be negative 1 over x to the 5th. And then we'll have minus a negative. (55) to the 5th power. All right, so we just plug in that value. This is not that bad. That goes to 0. So I get an upper estimate of my error, how far off I am from the actual sum, is about 1 over 55 to the 5th power. So just kind of check on that for a second in Desmos, see what it looks like. Before I go plug anything in. Desmos calculator. So I have my sum from 1 to 55. Remember, Desmos requires us to use an n, and this one is 5 over x raised to the, n raised to the 6th, excuse me. So the 55th partial sum is about 5.086. How many decimal places there are accurate? Well, the error to the actual sum is in the ballpark of 1 over 55 raised to the power 5, which is 1.9 times 10 to the negative 9. So 8 zeros, and then we finally hit a number. And our error is a little smaller than that. So we have 7 or 8 decimal places of accuracy here. So my sum, the actual sum is somewhere close to 1, 2, 3, 4, 5, 6, 7, maybe 8 decimal places. Oops, probably the whole thing. So up to the 3 or the 0, we have our accuracy based on that integral theorem remainder.